Okay, we're going to talk about some basic constructions. Constructions are traditionally done with a straight edge and compass. We'll also use patty paper sometimes to help us visualize constructions. But let's start with some terminology before we break out the tools. And so perpendicular lines are, it should be a familiar term, are symbolized with this, looks like an upside down T. That's supposed to show a right angle. It's two lines that form right angles, so 90 degrees. And then we have a perpendicular bisector of a segment is perpendicular to the segment at its midpoint, so bisecting into two congruent segments. That's similar to what we had before, and we have some notation to help us with that. So the midpoint, I know A is the midpoint of RT because I have these tick marks on it. And then these really should be points and not arrows if we want to look at this as a segment. And this is my 90-degree angle at A, so it's perpendicular, it's 90 degrees, and since it cuts it into two congruent segments, it's a perpendicular bisector of that segment. Similar to that, I have an angle bisector. So an angle bisector is a ray. So in this case, the ray is from B to C, and it divides my angle into two congruent pieces. Those arcs on them mean that they are congruent to each other. So that's an angle bisector. So we want to pay close attention to the notation with these two things as we get through it. We'll go through some of the constructions with the straight edge and compass as well, but we also want to look at how geometry looks on what's called the coordinate plane. So the coordinate plane should look familiar. We often talk about this coordinate plane as just graphing things. A coordinate plane has coordinates, traditionally x and y, and we have ordered pairs and axes and all sorts of good stuff that we want to make sure that we know and remember from our algebra class. So the x-axis is what runs horizontally, the y-axis runs vertically, and they meet at the origin. And so those are kind of my starting points as we go through anything with coordinates. I know x is left and right, y is up and down, and where they cross is going to be our ordered pair 0, 0. We're given names for these quadrants. So we can see that I've broken up into 1, 2, 3, 4 quadrants, quad meaning 4, and I label them just like that. So I have 1, 2, 3, 4. So if I say I have something in the third quadrant, it means that I would start it here. I go back and down. Back is a negative x value, down is a negative y value. And so I know that if I have something in quadrant 4 over here, it's a positive x value, a negative y value, which will get me to that quadrant. So ordered pairs are important. We want to make sure that we understand how they work. You've had a lot of practice with them before. We won't spend a lot of time reviewing. And also below, you've seen something like this, which is the distance formula. Down the road, we'll look at how it works in terms of the Pythagorean theorem. But the distance between 2 points, x1, y1, this is just notation. When it's a subscript, is x sub 1, or the first x value, corresponding with the first y value. And then I have the second x value and the second y value. And to get the distance, it's the square root of the subtraction, the difference of my x values, quantity squared, plus the difference of my y values, quantity squared. So you've used this before. We'll use it again. We want to make sure that we're fluent kind of with how that works for us. We also have a midpoint formula. So again, the midpoint is going to get us the coordinates, the ordered pair that are in the middle of a line segment form. And it looks like a similar setup. It is, I have x1, y1, x2, y2. But since I'm looking for a point, my output is an ordered pair. So I add the x values divided by 2. That's also the average. I average the x values, I average the y values, and I return an ordered pair. Whereas with the distance formula, I got an actual value, a number that I was looking for. So here's two examples. I usually start with labeling things x1 and y1, x2 and y2. Helps you keep it in order in terms of what you're subtracting. And then we plug in our values and see what happens. So that's my general distance formula. And then I plug in x2 and x1. And I get 6 minus a negative 2. And I get negative 2 minus 6. Now the hardest thing here is to think about subtracting negatives. So subtracting negative 2 is the same as adding 2. So I get 8 squared. And then negative 2 take away another 6 is negative 8. When I square both of those and I simplify the radical, I get 8 root 2. All right? So that's my distance. I don't have units. I don't know if it's feet, miles, inches. But I get the magnitude of the value. I want to find the midpoint. I can leave it the same in terms of x1 and y1, and I just put in my values up here. I'm going to average the coordinates. So -2 plus 6 over 2, and then 6 minus the -2 over 2. Simplify it, and I get 2, 2 is the midpoint as we go through this. The next one is the same idea, except I'm not given both the points, I'm given a midpoint. I'm given one of the points, and I want to find the other point. So this is my midpoint, right, my formula up here, where I have x1 and then an x2, but my problem is I don't know what x2 is. So we're just going to have to label point G with some general points, x and y, and we'll have to figure out what those are. So I plug in those values. That's my expression, and I know the value of the midpoint. It should be -6, and it should be -3. So I get two equations from that. 1 plus x over 2 equals -6. I solve for x. I get x is -13. And then I get another one, 4 plus y over 2 equals -3. And I get y, it'd be -10. So my ordered pair, my coordinates are -13, -10. That will give me the correct midpoint as we go through this. So there's my solution. My endpoint is going to be an ordered pair as well, because we're talking about midpoints and points within those segments. All right. We also have some formulas that look familiar. The perimeter of a polygon. So a polygon is a closed shape. We have some very familiar ones down below. It's the sum of the length of the side. So if you were to walk around the outside of any of these, you would get the perimeter. I would get the perimeter. I would get, in this case, we don't really call it the perimeter for a circle. We have a different term for it, which is going to be circumference. But it's the same idea. As I go all the way around, I want that distance. So it's a linear distance. The area of a polygon is the number of square units that it encloses. So if we imagine if I was to paint this shape, or paint this shape, or paint this shape, how much square units, how many little squares I filled up, that's what we call the area. And we have some formulas that, again, look familiar as we go through this. Perimeter, area, these are things that you've seen before. We will get more complicated areas, formulas as we continue down the road, but for now these are pretty straightforward. So this is similar to something that you might see where it combines our coordinate plane with our vertices. With our area formula. So we want to start with the picture. I have A, B, C, and D, right? I want to find the perimeter. So that's what it looks like. And perimeter, again, I'm looking for distances. So I know those are a distance of 2 because I can just count them. They're horizontal. So I see the distance 2. Really what I'm looking for is what's that distance going to be? Well, I can figure that out with the distance formula. It's going to be the same for AB, so I can just double it when I find it. And we use our distance formula. So if I look at AB, I set up my distance formula. I plug in 0, 0. That's going to be helpful. So that's my origin down here. I plug those points into my equation up here. And then I'm going to pick point B. So 9 and 12. If I run through it, I get 81 plus 144, which means it's 15. So if I get the perimeter of my whole quadrilateral, in this case it's going to be a parallelogram, I get 2 times 2 because there's 2 sides here that are 2, and then I get 2 times 15, and so 34 is going to be the perimeter. I don't have any units on this. I should probably put just units. It's a linear distance, but for right now 34 is what we're looking for. All right, we have some additional postulates. Postulate 1.9 means that if two figures are congruent, then their areas are congruent. Well, let's actually change that a little bit. We're going to say that the areas are equal. And the reason that we don't want to say congruent is because an area is a quantity, and so an area is going to be the same quantity as another one. So again, congruent figures mean they're the same, which makes sense they should have the same area. Postulate 1.10, the area of a region is the sum of the area of its parts, all right, that don't overlap. So if I was to look down at this figure and look at, that should be a 22, all of these non-overlapping figures, I see 2 rectangles and a semicircle. If we add those up, we get the whole shape. That should be pretty intuitive as we go through this. So we can figure out half of the circle, right? So that's supposed to be half of a circle, not a D. But it's half pi r squared, where my radius is 5. Okay? And then, so I get 12.5 pi. If I look at the red rectangle, it's 22 times 2, and I got the 2 because this is 8, this whole thing was 10, so that has to be 2 there and 2 here to make up that difference. So that's going to be 44, and then for the green one, it's 8 by 24, 192. To get the sum of the whole figure, I add them all up as we go through it. All right, that takes care of chapter 1.